Okay, hopefully everyone can see that. So this talk is joint work with my supervisor, Kevin Leyton-Brown at UBC, as well as Paul Milgrom and Ilya Segal at Stanford. 3 years ago, the FCC held a novel spectrum auction where the goal was to repurpose radio spectrum from broadcast television to wireless internet. And the way this was done was that the FCC selected some amount of spectrum that it wanted to clear, and it ran a reverse auction that bought spectrum from TV stations and then ran a forward auction that sold the spectrum that it bought to wireless carriers. And because TV spectrum was being reduced, some stations had to be repacked to fit into the spectrum that remained. So electromagnetic interference constraints prevented stations from jointly broadcasting in the smaller set. And in practice, 14 such TV channels were actually resold as 70 megahertz of wireless internet licenses for nearly $20 billion. And about 10 billion of these dollars were paid to TV stations to voluntarily give up their broadcasting licenses. Now, was this a good auction outcome? How would you go about analyzing that kind of a question? The gold standard, of course, is theoretical analysis, but this is such a complex, crazy setting that in this case, except for some maybe small theorems, this just seems very out of reach. Now, this paper is part of the AI track, and as many of us in AI know, Moore's law has continued. Compute power is becoming more and more available and cheaper. And what's so amazing today is that we're at a tipping point where simple algorithms running at scale can do truly amazing things. So what I'm going to propose in this talk is a philosophy of market analysis using computationally intensive simulations. And I want to highlight that this is an incredibly general tool that you can add to your toolbox when analyzing markets in complex settings. Now I'm going to ground this particular talk about the incentive auction design. And this is a good candidate for this kind of analysis because it was a novel, extremely complex auction produced under time pressure. And that leaves us with a lot of questions about which elements of the design were most important. And there's a lot of ripe, underexplored changes and alternative designs to look at. And so I hope you'll find the specific insights about the incentive auction design that I'm going to present interesting. I hope that they'll generalize to other markets that you care about too. But what I'm really advocating for here is computationally intensive simulations should be a tool in your toolbox. So what do I mean by simulation methodology? Well, the first step is to build an auction simulator. And here you get to choose to have as much fidelity as you'd like. So you can make minimal assumptions and just literally implement the auction rules exactly as stated, perhaps. The second thing that you're going to need is a parameterized bidder model. And some parameters are going to feed into be strategic parameters, and others are going to have to deal maybe with valuations. And once you have these parameters set up, you need a way to sample from them. Once you can do this, you can sample many bidders, bidder value profile pairs, and run simulations holding one aspect of the design fixed and changing some rule of the auction design. And lastly, you want to compare the outcomes that come from these paired simulations. So let's talk a bit about the incentive auction, since that's what we're going to be simulating in this talk. In a bit more detail, the way it worked was the FCC decided it wanted to clear as much spectrum as possible without losing money. So the way that it did this was it chose an initially large number of channels that it was going to clear. It then ran a reverse auction for TV stations. This determined the clearing cost. It then ran a forward auction for wireless companies, and this is just a typical spectrum auction like those that have been run before. And that's going to determine how much they would pay for this cleared spectrum. It then terminates if the forward auction can pay for the reverse auction. Otherwise, it decides to clear fewer channels. So it's going to add channels back to the TV band and resume the reverse auction. So as I said, the forward auction is kind of just a standard spectrum auction. The novel part is mostly this reverse auction. And so the way that it worked is that stations are initially offered prices for their licenses, and they can either accept or reject these prices. Stations that reject these prices exit the auction, meaning that they're going to go back on the TV band and they can never rejoin the auction again. Afterwards, auctions get approached in sequential order. First, we check whether a station can still fit inside the TV band. If it can't, we're going to call that station frozen, and it's going to stop lowering its price. Otherwise, it can still fit along inside the TV band alongside all of the stations that have already exited the auction. And if that's the case, we offer it a lower price, maybe 5% less than the price we offered it last time. If it accepts the new price, great, it continues in the auction. If it rejects the new price, it will exit the auction forever. What I hope you can see is that over time, the prices are going to lower, more stations are going to exit the auction. Eventually, some stations won't be able to fit inside the TV band, and the auction will end at a point in which every station has either exited the auction or is frozen. In order to actually instantiate and build a simulator, as I mentioned, we need a bidding and value models. So we're going to assume that bidders myopically maximize their profit in every round. And for the value models, we actually relied on 2 different value models as a robustness check to test our results. The first value model comes from the literature, from a paper that studies the similar setting. And the second value model we designed from bid data. So 2 years after the auction terminated, the FCC publicly released the bid data from the auction. And what we did is we assumed that station values are proportional to population, which is a known proxy for station value, times noise. By noise, I mean something sampled from a distribution. And in order to actually fit this distribution, we interpreted the bid data as censored value observations and then used a non-parametric method to fit the noise distribution. More details are available in the paper. Lastly, our methodology requires us to define some metrics in order to compare auction outcomes. We define 2 metrics to minimize. The first metric is value loss, which is the sum of values of stations that get removed from the airwaves. You want to minimize this metric, or equivalently, you can think of maximizing the value of stations that remain on the airwaves. You want to preserve as much value as possible. The second metric is the cost of acquiring spectrum. This is the amount of money that's paid to winning stations. With all this set up in place, I'm now going to talk about some experiments that we ran in the paper. The first question that we asked had to do with repacking VHF bands. So up until now, I've told you that stations could either choose to continue broadcasting or to accept money to go off the air. But actually in the auction, there was an intermediate option. Stations could accept some money and also move to a less desirable band called VHF. This provision, however, makes the auction rules significantly more complex, and it undermines some desirable theoretical properties. For example, it's no longer obviously strategy proof, even for single station owners. We wanted to understand, did this extra complexity actually help? And if so, was it worth doing? So in this graph, what I'm showing you now are on the x-axis, our value loss metric, and on the y-axis, our cost metric. And every point on this graph is a simulation. So this is a full simulation of the entire reverse auction, including all of the checking whether stations are frozen. So each of these points takes quite a while to generate. And what I'm showing you here is one simulation with VHF, one without VHF, and these points are paired, meaning that they're using the same input value profiles. Of course, we don't want to make any conclusions based on one simulation, so we need to add more. But what happens is that if you add more simulations to this graph, it becomes very difficult to tell, visually at least, which points are paired, which points are using the same inputs. Our solution is to show graphs in this format, where we're normalizing by one pair in each, or one sample in each pair. Putting all our samples together, we can now see that on average, the star is indicating what the average effect was. These UHF only auctions, that is auctions that do not repack the VHF bands, wind up costing 1.12 times more and experience 1.04 times value loss compared to those that did. The last thing that I want to highlight is that these results, this experiment that I'm showing you right now, took about 1 CPU year worth of computation. And I'm going to continue to show these numbers on the top right corner of the slides. The second question that we were interested in concerned the feasibility checker in the auction. So as I mentioned, during the auction, we need to continuously check before we lower a station's price whether or not it can fit inside the TV band alongside all of the stations that have already exited. And in practice, this is actually kind of a hard graph coloring problem. So on the right of the slide, I'm showing you an interference graph of the United States, where every node in that graph is a station, and there are edges between stations if there are interference constraints in between them. And as you can see, it's kind of a mess. And so we worked pretty hard before the auction to build software that could really effectively solve these graph coloring problems, because they needed to be solved thousands of times throughout the auction in real time. And eventually, we came up with a solver that, at least on benchmark problems, performed much better than other alternatives. But one question that we had remaining was, did this actually matter to economic outcomes, and how much did it matter? And without simulations, this is a very hard question to answer. So what we did is we ran simulations using various feasibility checkers. And that's what you can see plotted here. What you're seeing is that everything is actually to the top right of set of C, which is that red point at 1, 1, which we're normalizing by, meaning that it outperformed every feasibility checker. And what's especially cool is that it even outperformed the next best off-the-shelf feasibility checker so much that if you'd run auctions using that next best checker, they would have cost and experienced about 1.3 times more value loss. And remember that the scale of the auction is in the billions of dollars. So it was cool to see that actually our effort in investing into a custom feasibility checker seems like it paid off. The third question that I want to talk about concerns setting station-specific opening prices, also known as scoring rules in the auction. So in this auction, not every station faced the same opening price. In fact, they faced distinct opening prices. And afterwards, prices fell by about 5% each round. So in the auction, prices were increased for stations that had a lot of interference constraints, and they were reduced for stations that served smaller populations. The reason that you might want to do this is, for example, that if you have a station that causes a lot of interference and you offer it a high price, you'll delay its exit. And if it exited early, it could wind up freezing other stations at high prices. You might want to offer lower prices to stations that are likelier to accept them, just in order to reduce costs and minimize the risk that they'll freeze at high prices. That second point was pretty contentious and condemned by some as price discrimination. On the top right of the slide, you can see someone literally lobbying against this. So we wanted to understand, did these population adjustments actually reduce the cost as intended? We ran simulations using 4 different scoring rules or methods of setting opening prices. And we were able to find that, in fact, if we'd only used these if we'd only used this interference-based scoring, or if we'd let head-to-head competition set the prices and set every station opening at the same price, we would have done worse. So the FCC's combined scoring rule in this red series called incentive auction actually led to the best outcomes. The last question that we talk about in this paper concerns the FCC's procedure for determining how many channels to clear. And the FCC determined this using market forces. So this was an endogenous parameter in the model. It didn't come out and say, we're going to clear this much spectrum. It instead had this whole process that I talked about earlier, which alternated between stages of the reverse and forward auctions. And in practice, 4 of these sort of reverse forward iterations happened in the actual auction. We wanted to understand, how did this clearing procedure compare to predetermining the number of channels to clear? And to figure that out, we ran 2 sets of simulations. The first set followed the path of the real auction, first trying to clear 21, then 19, then 18, then 14 channels. And the second set of simulations ran only a single stage, clearing 14 channels, equivalent to perfectly forecasting demand. What we found was that these 4-stage auctions were actually 1.14 times more costly and experienced 1.14 times more value loss than single-stage auctions. And this was surprising because, unlike the previous question that I've showed you, we couldn't find pictures of people lobbying to try and make the claim that this was sort of a part of the auction design that more focus needed to be thought about. This is really part of an innocuous seeming part of the design, where after running these simulations, we suddenly realized that actually there are some potentially big losses here. To give you some quick intuition for why this might happen, imagine that we have 3 stations, A, B, and C, and you can see from the side where I'm showing their values and their prices, station A has a higher value than B than does C, for example. Let that blue box be the TV band, and the green area is the area that we're going to clear and sell to wireless spectrum. As the auction proceeds, station A is going to exit once its price falls below its value. Once it does so, B can no longer fit inside the TV band. It is now frozen, but C still has room to fit inside the band, so its price will continue to lower and it will eventually exit the auction. At this point, the reverse auction is finished, and we go to the forward auction. We ask the mobile companies how much they're willing to pay. If the mobile companies are not willing to pay the amount that we would have to pay the TV stations, in this case B, to vacate their licenses, we add more spectrum to the TV band and go on to the next stage of the auction. Imagine that the next stage looks like this. We've added more spectrum, we resume the auction, but B is still frozen, so we can't really do anything about it. But notice that if we'd known that that first stage was going to fail, and if we just started with the right amount of spectrum available, we would have actually achieved this outcome. A would have exited first, B would have exited second, and C would be the one to be frozen. This is a lower valued station being frozen at a lower price, so a better outcome according to both of our metrics. So motivated by this example, we wondered about whether a small amendment could help the clearing procedure. What if we actually just ran the forward auction before the reverse auction? If you did this, you would already know how much the mobile carriers were willing to pay for that amount of spectrum, and you could stop the reverse auction immediately once the clearing cost exceeded what the wireless companies were willing to pay. Going back to that example, notice that at this point, why would we continue running the auction just to let C exit when this is an irrevocable commitment that we can never change in later stages? We could just stop right here, add the new spectrum, and we would get the outcome that we desired. So we ran simulations using this early stopping algorithm, and we saw outcomes that were very similar to perfect forecasting. So that gap that I showed in the previous image was nearly completely eliminated. And furthermore, when compared to the standard clearing procedure, in our simulations, we observed that early stopping auctions led to clearing more spectrum, which was one of the FCC's stated goals in running the auction, and it did so in fewer rounds. This was an auction that took place over 13 months, so it was already quite a lengthy auction, and this early stopping algorithm maybe could have made it shorter. In conclusion, what I want to advocate is that large-scale statistical analysis of complex markets is actually a practical tool that you should have in your toolbox when evaluating market designs. I used the incentive auction as a concrete example and talked about 4 problems and questions that we had. We found that repacking VHF lowered costs. We found that it was worth investing in a custom feasibility checker. We found that population scoring worked as intended. And we noticed that running the auction over multiple stages might have been a big problem for cost and efficiency, and proposed an amendment that could have combated these losses. These experiments used about half a century of computation. That's only including the final experiments. Of course, I messed up many times and had to rerun them, so you want to double, triple, quadruple this number a bit. But on modern cloud computing, that's actually pretty accessible. Our final experiments maybe would have cost about $100,000 to run on Amazon. That's not nothing, but given the scale of the auction, that's totally within reach. Thank you.